Welcome to 3.3, zeros of polynomial functions. So what is, or how do we determine the number of zeros of a polynomial function? Well, we've mentioned this many times, and we always look at the degrees, right? The degrees of our polynomial, and that will help us determine the number of zeros. So a polynomial function p of degree n has at most n zeros. So a degree 2 polynomial has at most 2 real zeros, where each zero has a multiplicity k is counted k times. So we'll talk about what that multiplicity is. So that's kind of our new aspect today. So just like the last video, we're going to look at polynomials and we're going to draw a potential graph or a sketch around the zeros. Okay, so let's find the zeros of the polynomial function and state the multiplicity of each zero. Then we'll graph each of them. All right, so if we take a look, it's already factored for us, right? And so here we go. We can say it's a degree 5 because we have a degree 3 times a degree 2. So that's where we get 5 from, adding those two powers. It's going to be a positive leading coefficient, all right, because the leading coefficient of this x is positive and this x is positive. So it's a positive leading coefficient, odd degree, so we know it's going to look like a line with a positive slope in the end. Okay, so what are the zeros? Well, just like before, we set each factor equal to 0 and we solve. So we get negative 4 from that guy. Now, this is where I look at the degree. It's a degree 3 here. So this is known as a multiplicity of 3. So that's the new terminology today. And just like before, we know since it's an odd power, it's going to cross our x-axis at that point. Our other zero is going to be 1. This is an even degree, degree 2, so it's a multiplicity of 2. And again, since it's even power, it's going to bounce at x equals 1. So if we wanted to graph this, we know it's going to look like this in the end, so I'm going to start down, okay? Now, one thing we should notice, and I'm not going to be too worried about this for this class, is notice that this has like a little dip here at x equals negative 4. Because it's a multiplicity of 3, around that point, it looks like a cubic function, an x to the third power. Okay, so it's got this little blip. Again, I'm not going to be too concerned with that guy. So we're going to cross, and at some point we've got to come back down, and at x equals 1, we're going to bounce. So I hit it, and I bounce back up, and there is our graph. Okay, so the new terminology today is multiplicity. Let's take a look at this next graph here. All right, so one thing that's a little bit different about this guy, x plus 4 squared times x squared minus 9 squared. What you should notice is we can factor x squared minus 9 a little bit more, right? So when we factor that, we really have this x plus 3, x minus 3. But that whole thing is being squared. So we really have these brackets here, okay? So since both of those factors are being squared, we can distribute that power to both of them. So really the full-fledged factored version of this polynomial is right here. X plus 4 squared times x plus 3 squared times x minus 3 squared. So we have ourselves a degree 6, adding up all of these powers. They're all positive leading coefficient, so I'm going to picture a quadratic opening up. Okay, so in the end, it'll look like this. The middle part is what we're going to graph. So now we have to talk about the zeros and the multiplicity. So from this factor, I get a 0 of negative 4. Looking at the power, I have a multiplicity of 2. Since it's even, I know it's going to bounce there. Looking at this factor, I have a 0 of negative 3. The power is 2, so I have a multiplicity of 2. Again, we're going to bounce. Looking at this last factor, I have a 0 of 3. Multiplicity again is 2 because of my power here. And again, since 2 is even, I know I'm going to bounce. Go ahead and try to graph this. Check back after you get a chance to do it. Okay, did you get something like I have over here on the right? I know the end behavior is going to be pointing up. I come down, I have to bounce at x equals negative 4. I've got to come back down and bounce at x equals negative 3. And then I got to make my way over to bounce at x equals positive 3 and go back up. Notice I didn't touch my x-axis at any other point besides those 3 zeros. The next thing we're going to look at is finding all the zeros of a polynomial function algebraically. We'll need a little help from our calculator, so make sure that's handy. So, first thing we do is we gather all the general information. We determine the degree, which will help us determine the number of zeros. We're going to use our calculator to find 1 zero. So you'll plug the equation into y equals, and then you'll use your table of values. We'll then go and use synthetic division to reduce the polynomial to a quadratic. Sometimes we have to do this 2 or 3 times. Okay? Then we'll solve the reduced quadratic polynomial by factoring when possible or a quadratic formula. Okay? So let's look at our first example here. Here's our polynomial. I notice it's a degree 4, so in the end I should have 4 zeros. Okay? All right, so I'm going to plug this into y equals. I want you to pay close attention, try your best, and we'll go through the calculator portion if you're having trouble in class next time we see each other. So I plugged this into y equals. Then I went to my table of values, and I'm looking for the x value where y equals 0. So as I'm scrolling through my table, I notice that when x equals 1, in my table, y equals 0. So remember, when we're using synthetic division, that x value goes in our box, in our corner. -1 goes in the corner. I look through to make sure I don't need any placeholders with my synthetic division. So remember, I start with a degree 4, I have a degree 3, then 2, then 1, then 0. So I'm not missing anything. I don't need any placeholders. Remember, we drop the 3, then we multiply, then we add to 20, multiply to -20, add to 36, multiply to -36, add to 16, multiply to -16, and we get 0. Remember, when we get 0 as our remainder, this means we have ourselves a factor. So if -1 is the 0, x plus 1 is our factor. And we have this as our remaining polynomial. So I have 3x cubed plus 2x squared plus 36x plus 16. Well, the rule stated I needed to use synthetic division to reduce to a quadratic. I don't have a quadratic quite yet. So what I need to do is I need to go back to my calculator, my table of values, and I need to find another 0. So when x equals -2, I notice in my table of values, y equals 0. So that works. So -2 goes in the corner. Now I'm going to take this polynomial that we found from above and put those coefficients in for synthetic division. So 3, 20, 36, and 16. We carry out our synthetic division operation, and I'm left with this quadratic now, 3x squared plus 14x plus 8. So notice though, since -1 was a 0, x plus 1 was my factor. Since -2 was my 0, x plus 2 is my factor. So now I'm getting down to this portion here. So now I can go to step 3, or sorry, our step 4 here, is solve the quadratic equation, okay? So I can actually factor this, setting it equal to 0. It factors nicely, and I get 2 zeros here. So if I wanted to talk about the factored form, here's the factored form of our polynomial, but it was asking for us to find all of the zeros. So all of the zeros are going to be -1, 0, -2, 0, -2/3, 0, and -4, 0. Those are the ordered pairs. If you simply listed the zeros as -1, -2, -2/3, and -4, that would certainly work. I want you to try this last example on your own. Give it a try, go through the process, solve completely for all of the zeros, and then check back with your answer here. Take a look at what I did, and yours might look different if you used a different 0 to start with, okay? But in the end, what you should get is the same quadratic that I got down to, okay? And then when we go through and you solve the quadratic, it does factor very nicely, so we can then list all of our zeros. If you have questions on this, make sure you ask in class next time we see each other.